In this final video for Chapter 15, we want to look at the basis for the Huckel rule. So why is it that the number of electrons determines whether a compound is aromatic? Is it not enough for the compound to be completely conjugated, planar, and cyclic? Why does it have to have that specific number of electrons? Just as to review our two primary examples here, over here on the right we have benzene. Benzene is cyclic, planar, completely conjugated, and it has 6 pi electrons, and therefore it is aromatic. Cyclobutadiene also is cyclic, planar, completely conjugated, but because it has 4 pi electrons, we're going to consider it antiaromatic. In order to do this, we're going to look at orbitals and bonding. And we're going to do something a little bit different than the valence bond theory that we have been looking at for quite a long time. We're going to use something called molecular orbital theory. Now, just a quick comment about valence bond theory. Valence bond theory, it is a very convenient way of looking at bonds. We discuss bonds in terms of individual orbitals on individual atoms that overlap to give us either sigma or pi bonds. Again, it's very useful. We use it all the time, but it doesn't explain everything. It has trouble dealing with this whole aromaticity issue. Fortunately, we have MO theory that will help us to understand this a little bit better. So we're going to look at molecular orbitals, or MOs, as orbitals that are not localized on individual atoms, but rather they are orbitals that are over several atoms, sometimes 2, at least 2, but sometimes 3, 4, 5, and in the case of benzene, 6. All right. We'll find that a molecular orbital occupies a region in space that is around several atoms, and again, it's not going to be around single atoms, it's going to be around multiple atoms. So let's look at how it is that we form molecular orbitals. Well, when we're doing this, it's first important to remember that however many atomic orbitals we contribute to a molecular orbital system, a set of molecular orbitals, we're going to have the same number of molecular orbitals as we have those atomic orbitals. So for example, if we have 2 atomic orbitals that combined, we're going to get 2 molecular orbitals, one that will be lower in energy and one that will be higher in energy. Now recall, for aromaticity, we're talking about pi bonds, so we're talking about p orbital overlap, side by side p orbital overlap. That's going to be different than all the sigma bonds, because there's lots of sigma bonds that are in benzene or other aromatic systems, but here we're interested in just the pi bonds, so we're looking at just the p orbitals. Now, one thing that I want to note about the shape of a p orbital, and I'm going to show you the shape of a p orbital here. I've got it drawn out. It is drawn literally by my hands here. So this is what a p orbital looks like. It is dumbbell shaped. And I've drawn 2 different colors here to represent the 2 different parts of this. These are different parts of the wave function. One is essentially the trough and one is the peak. Now, which one is which, it doesn't really matter because they act the same. They both have the same electron density in them. It's just that this part and this part are in opposite phases. What we mean by that when we say they are in opposite phases, over here I have a standing wave on a string. So a string that is stretched between these 2 points, and you can see that the string is vibrating back and forth. From here, it just looks like it's in the up position, but if you were to look at it over time, you would see that it would vibrate back and forth, and it would be kind of a blur right here. All right, this is called the fundamental. It's the lowest harmonic of a wave function, of a standing wave. And so that is, this has no nodes in it. If we take that same string and we pluck it, we will find that it can vibrate in another fashion. This is another energy, and here we'll have part of the string that will be up and part of the string that will be down, and they will be opposite phases of each other. And again, it will look something like this. All right, so it'll look something like this, and we'll have a node in the middle. It will look, if you were looking at this kind of with a camera or something, it would look as if this part is standing still, and this is vibrating back and forth, and this is vibrating back and forth. The important thing to remember is that this part and this part are going to be in opposite phases from each other. And that's what we mean when we put the two different colors here. They are in opposite phases. Okay, so a p orbital has a node, and it has two parts, two lobes, that are in opposite phases. So let's go back to our thing, and that's what I'm talking about here. They are in opposite phases. Now, if I take two of these orbitals, again, so if I take two of these and combine them together, there are two ways that you can combine two of these orbitals together. And those two different ways are going to give us our bonding and antibonding molecular orbitals. All right, so when we say that there are two ways, we can combine the two orbitals so that they give us what we call constructive interference or constructive interaction. And in this case, because the peaks are aligned with each other and the troughs are aligned with each other, the two phases are aligned, that means we get constructive addition of these, and we get overlap above and below our sigma bond, and that makes up our pi bond. Well, this is only one of the possibilities. The other possibility, and again, we call that a bonding molecular orbital. The other possibility is when they are in opposite phases, and this is the case here. They're in opposite phases, and when that happens, when we put the two orbitals together, since they are in opposite phases, they essentially have a destructive pattern or destructive addition. So they cancel each other out. Well, we refer to this as a pi star or antibonding orbital. So whenever there's a star, we call that antibonding. So there we go. That's the antibonding, and this is the bonding. So the important thing to remember is that both of these orbitals exist when we put two p orbitals by each other. We get both the bonding molecular orbital and the antibonding molecular orbital. They exist in the same space at the same time. The only thing is that when we form a pi bond, we usually only put electrons into the bonding molecular orbital because it is lower in energy. So let me show you what that looks like. All right, so just as a reminder, when we have atomic orbitals, the number of atomic orbitals needs to equal the number of molecular orbitals. So you'll notice here on the sides, we have two p orbitals that are far apart from each other. When we bring them closer together, we're going to create two new orbitals, and these will be molecular orbitals. So these p orbitals essentially disappear. Now, they're not really gone, they're there, but we don't see them anymore because we see the molecular orbitals. We'll get the one that is lower in energy. That one is referred to as the bonding molecular orbital. And the one that is higher in energy is the antibonding molecular orbital. To the extent that we put electrons into a bonding molecular orbital, we're going to get a pi bond. In this case, a pi bond. To the extent that we put electrons into an antibonding orbital, like this one up here, it's going to cancel out the pi bond that we made here. But fortunately, because of the rules of molecular orbitals, or orbitals in general, when we take these two electrons and we put them into an orbital, they're going to go to our lowest energy orbital first. And so in the ground state, when it's in its lowest energy arrangement, the electrons are going to be in the bonding molecular orbital. The difference in energy between that bonding molecular orbital and the antibonding molecular orbital, that difference in energy is going to be equal to the energy required to excite an electron from this orbital up to that orbital. So in a previous chapter, we talked about conjugation and ultraviolet, absorbing ultraviolet radiation in UV spectroscopy. And we found that when we have a single unconjugated pi bond, like in ethylene, that the distance between these is pretty big. And so you have to have a very high energy photon to excite one of those electrons. If you conjugate it, these orbitals get closer together. And we're going to see what that looks like when we look at benzene here in just a moment. All right, the molecular orbital diagram for benzene is a lot more complicated. There's more to it. So when you look at this, number one thing is just take it in, maybe pause the video so you can have a good look at it and see what's all involved. Since we have 6 carbons with p orbitals on a benzene ring, that means we're going to have 6 molecular orbitals. All right, and so these are the 6 molecular orbitals. 3 of those orbitals will be lower in energy than our p orbitals that we started with, and 3 of them will be higher in energy. So there's the 6 orbitals. We number these orbitals from the lowest energy up to the highest energy using the Greek letter psi. So psi 1, psi 2, psi 3, 4, 5, and 6. Psi 1, 2, and 3 are low, or psi 1 is the lowest in energy, psi 6 is the highest in energy. Now, there's a couple of features about these that I want to point out. Our 3 lowest energy, psi 1, psi 2, and psi 3, the ones down here, these are bonding molecular orbitals. The antibonding molecular orbitals are the ones that are higher in energy than our original p orbitals. All right, and there's a couple of important features that I want to point out. The larger the interaction, so the more overlap that we get, the lower the energy is going to be. And so if you notice down here in this lowest energy orbital, we'd have no nodes. At least we have a node that's in the plane of the molecule, but we don't have any nodes perpendicular. And so you'll see all of these p orbitals are in phase. As we go up to each higher level, for these two, psi 2 and psi 3, we have a node. There's a node on this one that goes right through these bonds. So you'll notice these 3 are in phase and these 3 are in phase. And in this one, the node is perpendicular. And so these 2 are in phase, these 2 are in phase. And at these 2 carbons, we have no p orbital density in that one. If we go up to the next one, we end up with 2 nodes. Here on this one, there's one that goes through here and one that's perpendicular to it. And so you'll see that there are no overlapping interactions here. On this one, they kind of cross each other. So we get a node here, here, there, there. And there's actually two nodes, one that goes across here and one that goes across there. So 2 nodes. We do get some overlap there, but this is equivalent energy to this one. And then finally, when we go to that highest energy one, you'll see there are lots of nodes. There's 3 nodes. There's one there, one that's there, and one that goes across there. You'll notice none of the adjacent p orbitals are in the same phase. So we get no bonding interactions between any of those. To the extent that we put electrons into these lower energy orbitals, we get bonding, we get pi bonds. And to the extent that we put electrons into these higher energy orbitals, we get antibonding, and it cancels out some of the strength of these bonds. Equal energy orbitals, we use a special word to indicate 2 equal energy orbitals. We talked about this word back in general chemistry, but it may have been a while. So those 2 equal orbitals, we call them degenerate. They have the same energy. And then one other thing that I want to point out is that we have these abbreviations, HOMO and LUMO. HOMO means highest occupied molecular orbital. So the highest occupied molecular orbital. You'll see of all the molecular orbitals, there's 6 orbitals here. These are the highest ones that have electrons in them. And then we have these that are called the LUMO, lowest unoccupied molecular orbital. The lowest unoccupied molecular orbital is the lowest energy orbital that doesn't have any electrons in it. And that's what we mean by that. The difference in energy between the HOMO and the LUMO is going to give us the energy needed to excite one of those electrons. And so if we want to excite an electron to put the molecule into an excited state, we need to add at least that much energy to do that. And by the way, one thing I will point out is that if you take a UV, what you're doing is you're exciting the electrons. You take a UV spectrum of it, and because this one's a more conjugated system, it's aromatic, we're going to find that the HOMO and LUMO are closer to each other than the bonding and antibonding orbital in ethylene that we saw on the previous page. All right, there's a couple of important rules that we need to remember anytime we're dealing with orbitals, whether it is electron configurations in just atomic orbitals, or whether we're talking about molecular orbitals, as we are here. First rule is the Aufbau principle. Aufbau is just a German word that means build up from the bottom. So you start at the bottom and work your way up. It literally means build up. It just means that when we're putting electrons, we start at the bottom and work our way up in process of filling them. Our second rule is called Hund's rule. Hund's rule tells us how we deal with degenerate orbitals. When we have degenerate orbitals like this, we singly occupy each of these orbitals first before we doubly occupy, meaning that we would have an unpaired electron here, and if we had 4 electrons, we'd have 2 here, 1 there, and 1 there. So we have to have singly occupied orbitals. You may remember this when we were doing electron configurations, and we talked about the p orbitals for something like nitrogen. If we have atomic nitrogen, there's 3 p orbitals, and it would have 3 unpaired electrons. Our third rule is the Pauli exclusion principle. It tells us that whenever we have electrons in an orbital, they have to have opposite spin. In other words, you can't have 2 electrons in the same orbital with the same spin. All right, so that's sort of our basics when it comes to MO theory. So we now want to figure out, well, how is it that we can come up with, I'm going to go back, the energies for these orbitals. How can we draw this so we get the energy for these orbitals? Well, it's pretty straightforward. We can use something that's called the Inscribed Polygon Method. And it's a very simple method that we can use for monocyclic, completely conjugated systems that are planar, and we can describe whether a system is aromatic, anti-aromatic, or not aromatic by looking at this energy diagram. First thing, however many atoms you have in your cyclic system. In benzene's case, there are 6 carbon atoms, so we'll have a hexagon. That's typically how we draw it, as a hexagon. We're going to inscribe a regular hexagon in a circle, as we have here, and we're going to put one of the vertices pointing down. And so here is one of the vertices that is pointing down, and that's going to be where the energy of our lowest molecular orbital. And then the other vertices are going to be the energies of the other orbitals. We'll draw a line horizontally across the middle. Anything that is below that line is going to be representing bonding molecular orbitals. Anything that is above are going to be considered antibonding molecular orbitals. And if we happen to have something that is exactly at that energy, then we're going to call those non-bonding orbitals. So we can use this method once we have the energies of our psi 1 through 6. We can use this as a way of predicting aromaticity. Again, Aufbau principle says we start at the bottom. Hund's rule says we singly occupy these degenerate orbitals first before doubly occupying. And then Pauli exclusion principle tells us that we have to have opposite spin electrons in each of those orbitals. All right. When we put that in there, we're going to find that if we put 6 electrons into these bonding orbitals, we'll completely fill our bonding molecular orbitals. 2, all of our electrons will be paired, so we'll have no unpaired electrons. And 3, we're not going to have any orbitals that are right here at the non-bonding level. And so that's going to give us our difference. Now, there are some limitations to doing the Inscribed Polygon Method. It only works for monocyclic, completely conjugated planar systems. If it meets all of the requirements where it's cyclic, completely conjugated, planar, then it has to also be monocyclic. So we can only have one ring. In other words, something like naphthalene, where we have two rings that are joined together, that's not going to work for this method. There is something we can do with that, but it's not going to use this particular method. All right, so the total number of molecular orbitals is always going to be equal to the number of vertices. So if you have 6 carbons, you'll have 6 vertices, so therefore you will have 6 orbitals. If you only have 5 carbons, you'll have 5 vertices. All right, and we're going to find that the inscribed polygon method is completely consistent with Huckel's 4n plus 2 rule, and it will also help us to explain the anti-aromatic rule that we get for things like cyclobutadiene. So we'll look at that here in just a moment. So here we're going to take 2 other systems, a 5-membered ring and a 7-membered ring, and look at those. These are 2 systems that we know are aromatic. So this is the cyclopentadienyl anion. Because it's an anion, there's 1 extra electron, and that 1 extra electron will give us 6 total electrons. When we put those electrons into our 3 bonding molecular orbitals, we will find that they completely occupy those 3 bonding molecular orbitals. If we use the tropylium cation, so 7-membered ring with 6 electrons, we'll see the same thing, that we get the 6 electrons that are in bonding molecular orbitals. One thing that's important here, we have no electrons that are at the non-bonding level, so that are exactly right here, and we also have no singly occupied orbitals. All of our orbitals are doubly occupied. It turns out that ends up being a more stable configuration. So looking at this helps us to explain our sort of magic numbers that we get when we have Huckel's rule, the 4n plus 2 pi electrons. If we have 1 orbital that's below the p orbital level, so it's below the non-bonding level, then we can only put 2 electrons in there. If we have 3 orbitals, we'll have 6 electrons. If we have 5 orbitals, we'll have 10 electrons. We'll see that it always starts off with 1 orbital on the bottom, which can have 2 electrons. That's the plus 2 part. And then our subsequent orbitals always come in pairs when we are doing our bonding molecular orbitals. So that's why we get 2, 6, 10, 14, 18, 22, so on and so forth. Let's look at number 19 on our in-class assignment. Go back over here to our document camera. So we just looked at the cyclopentadienyl anion, and I'm just going to go back to that real quick. So here, this is our cyclopentadienyl anion that is right there. So with 6 electrons, we ended up getting an aromatic system. We're going to use the same method to do the inscribed polygon method to do the cyclopentadienyl cation and radical and explain whether they are aromatic, anti-aromatic, or not aromatic. So first of all, we'll draw our inscribed polygon. All right, and that tells us where our orbital energies are going to be. So once we have that, we can just draw those orbitals again. So here, this is an energy. And we've got 1 that's down here, 2, and 2. All right, and we can refer to these. We can put in psi 1, psi 2, psi 3, psi 4, and psi 5. So let's start with the cyclopentadienyl cation. As we talked about before, it is a completely conjugated system. right? And we can draw 5 total resonance structures for this, one where we put that positive charge at different places, but we know that this only has 4 pi electrons, so it is anti-aromatic. Well, to explain why it's anti-aromatic, we're going to put in the 4 pi electrons. So we'll put 1, 2. All right, and again, you'll notice I put them in opposite spin here. And then Hund's rule tells us that we need to singly occupy these first. So I'll put 1 there and 1 there. And that gives us 4 electrons. Our energy breakdown is going to be like our sort of crossover between being bonding and antibonding is right there. So we're going to find that these are a little bit below that non-bonding level. So these are technically bonding orbitals, but you'll notice they're bonding electrons in bonding orbitals, but you'll notice that they're singly occupied. And we're going to find that this will be much more stable when these are doubly occupied. So this is anti-aromatic. So that is anti-aromatic. Now, we're going to do the same thing, but this one is going to be for the radical. So we're going to have a radical there instead of a positive or negative charge. That means that we're going to have 5 electrons in this system. We'll draw these at the same energy level. So psi 1 through 5, and because we have 5 electrons, 1, 2, 3, 4, again, Hund's rule tells us to do that. And then our 5th one, it doesn't matter which one we put it in. I'm going to arbitrarily put it into psi 2. All right. And you'll notice that this does not have 4n or 4n plus 2. It's got an odd number of electrons. It means we have 1 unpaired electron. It's more stable than the anti-aromatic because we only have 1 unpaired electron, but it is less stable than the aromatic system where, come back over here, where we had all of our electrons were in pairs. So all of them were paired. All right, so this one we're going to label not aromatic. All right, so aromatic for the cyclopentadienyl anion. So this one's aromatic. It's anti-aromatic for the cation, which is this one here. And it is not aromatic for this one because it has an odd number and it does leave us with 1 unpaired electron. Again, you can do this with any cyclic system. I encourage you to try this with a couple of different systems like that one. So this is the cyclopropenyl cation, also with the anion. All right, so there's that one. You can do it with the radical as well, but all the radicals are going to end up being like, they're going to be like this, where they're not aromatic. And you can try this with a couple of different systems. You can even do this with something like pyridine that we discussed earlier. That pair of electrons there. So with that, we're capable of doing the same kind of process. All right, we have one last topic that we want to look at before we finish up with this particular chapter, and that is looking at elemental carbon. Now, there are 2 common forms of elemental carbon. One is diamond and the other is graphite. Diamond is interesting because it has every single carbon in a diamond is sp3 hybridized and connected to 4 other carbons. And so it forms an essentially infinite, it's not literally infinite because otherwise it would be, you would have things that are bigger than the Earth. But here we're just going to say it's a very large system with an essentially infinite number. And if you have a perfect diamond, then all of those carbons are bonded to 4 other carbons. The only ones that aren't are the ones that are at the edges. And so that is sort of a different thing that's happening at the edges. If we look at graphite, all right, if we look at graphite, in graphite, all of the carbons are sp2 hybridized. You'll see that every carbon has a p orbital on it that's perpendicular to the sheet of graphite that is here. If we take graphite and look at how it forms when we have like graphite in mass, we'll see that it forms these sheets, and these sheets are not covalently bonded to each other. The only thing holding one sheet to another is intermolecular forces, dispersion forces, in fact. As a consequence, these sheets are capable of sliding past each other. And so, when we look at diamond, diamond is one of the hardest substances known, and it's because it's this extremely rigid three-dimensional array of sp3 hybridized carbons, and it's impossible to like move these atoms around significantly. I mean, you can, but not very easily. Whereas with graphite, because these sheets are capable of sliding past each other, we're going to find that it is actually very soft and that graphite is quite slippery. And in fact, graphite is used as a lubricant for locks. Typically for like a lock where you put your key in, you don't want to put oil in there because the oil will gunk it up. And so you can put graphite in there, and that will keep the metal lubricated because of the slippery nature of the graphite. So that gets us to a question. Are there other forms of carbon? And the answer is yes, there are other forms of carbon. And those other forms of carbon, the most important one is called fullerenes. And so we're going to look at something that's called Buckminsterfullerene. Now, Buckminsterfullerene, the question is it aromatic? When we look at Buckminsterfullerene, it's carbon C60, and every carbon is sp2 hybridized, meaning that there are sp2 orbitals that overlap to give us these sigma bonds between each of the carbons. Perpendicular to those are p orbitals, and so every one of those 60 carbons has a p orbital that is capable of being completely conjugated. Now, if you're having trouble seeing what this looks like, I have a photo. All right, I got this photo. I just downloaded it from the internet, and there is the photo of what this looks like. If you imagine each of the vertices here, each of these points is a carbon, and that so it's sp3 hybridized, and perpendicular to each of those points is a p orbital. So we're going to find that Buckminsterfullerene is cyclic and completely conjugated. So the question is it aromatic? Well, the short answer is no, it's not aromatic. It is completely conjugated, it is cyclic, but we will see that it is not planar. As you can clearly see, this is not a planar molecule. Because it is not planar, we're going to consider it not aromatic. That means if we want to do reactions where we add, where we can add things across the carbon-carbon double bond, we can do that in ways that we couldn't do with aromatic systems. So that Buckminsterfullerene, is it aromatic? No, it is not aromatic. All right, so now we're going to look at number 65, which is not about, it's not about carbon directly. It is a little bit different. This is a mechanism problem. We haven't done a mechanism problem in this chapter. I mean, we've done some arrow pushing, but we haven't done real mechanisms here. So we are going to do a mechanism. This is kind of a cool mechanism. We can take R carvone, which is a component in spearmint. If you'd have the L carvone, it's actually a component of caraway seeds. And they're enantiomers of each other, and they smell different, which is kind of cool. But if you're familiar with spearmint, you've tasted this. Well, this will undergo a acid catalyzed isomerization. So you can convert it into this compound. We want to do that mechanism. And the whole reason we're doing this is to kind of set us up for this next chapter where we are going to look at aromatic systems, and we're going to talk about how they work. So Let's start. Notice I have some hints here. Draw a stepwise mechanism and explain why this isomerization occurs. Well, the reason it occurs is it goes from something that is not aromatic, because it's not completely conjugated all the way around, to something that's aromatic. So that's the quick answer, is it's forming something that's aromatic. That gives it additional stability, and so we will get that compound. So let's draw this. All right, there is a hydrogen that is right here. So I'm going to draw that hydrogen because it's going to be important here in a moment. And then here we've got a carbon-carbon double bond. Now there are three different protonation, deprotonation steps that are involved with this. You can do them in other orders, but this is going to be the easiest way to do it. So we're going to start by protonating this with sulfuric acid. All right, so there is sulfuric acid. We're going to go from this pi bond, although this one's going to be the most easy to protonate. We're going to go from this pi bond over to that hydrogen, kick those electrons over. All right, so we get this carbocation. Well, this carbocation is going to be deprotonated. So we'll have OSO3H. We're going to go from here and deprotonate that oxygen, that hydrogen, which is why I did that. We'll take this pair of electrons and it will go to make a pi bond there. All right, so now we're going to protonate this one again. All right, so we're going to use that pi bond there. So I'll go from there to that hydrogen. All right, so now that we have protonated that, all right, so we protonated that, and we're going to have the hydrogen come out here. It can go to either, but only one of them is going to make any progress. So we'll have a carbocation that is there. Oh, I meant to do a methyl group there. All right. Here we've got two hydrogens, and we're going to deprotonate one of those hydrogens with our bisulfate. OSO3H minus. We'll come over and deprotonate that, and then we'll have a pi bond there. You notice that in doing that, we have extended our conjugation. All right, we're almost there. There's only one thing left to protonate, and we're going to protonate this oxygen. There's actually two resonance structures we can draw for that. I'll go ahead and do that. So we'll have hydrogen, lone pair of electrons. like that. I think I've got everything there. We're going to go ahead and put these hydrogens on because we're about to deprotonate that. But before we do that, let's draw one additional resonance structure where we put a positive charge here. Now, there's some other resonance structures where we can delocalize that positive charge, but we're going to put the positive charge here. And so we'll take one of the pi bond that's between oxygen and the carbon, and we'll kick it out to the oxygen to give us that. And then that's going to give us a positive charge right there. We'll go ahead and also put those hydrogens on there, and we're going to deprotonate that, and that's going to finish out our aromatic ring. So OS, OS. I got a little messy there. Let's try that again. SO3H, negative charge. So we're going to take this, deprotonate, and then we'll get a pi bond there. That's going to finish out our aromatic ring. And I'm going to put the pi bonds in the same location to avoid confusion, although you could put them in either of the forms. All right, and we get that as our product. All right, so there we go. That is the end of chapter 15. And in chapter 16, we're going to look at reactions with aromatic rings.